Check, check. Online students, can you hear me clearly? Online students, can you hear me clearly? Can someone please confirm? Okay, thank you. Uh, so today we have to start the lesson static electricity. Static electricity file. Static electricity file. Uh, and provide the tunes in the Zoom chat. Tunes ටික මේ Zoom chat එකේ දාන්න. Uh, so let's start with static electricity, ස්ථಿති විද්‍යුතය. So we have already finished the gravitational fields lesson. Okay, we have finished the gravitational field lesson. So this is another field, another similar field. Okay, lot of thank you, lot of like behaviors of static electric fields are almost similar to the behavior of a gravitational field. Okay, so the behavior is very similar, and you'll understand the reason. Okay, towards the end of the lesson, you will understand the reason, but both are like almost similar. So what are gravitational fields? Gravitational fields are the fields that exert forces between a mass, right? Between the mass. Clear? Okay. So if an object have a mass, a gravitational field would create a force on it. Clear? The same way, static electric field is a field that exert a force on a charge. Clear? A static electric field is a field that creates a force on a charge. Okay. So, like general things that we see related to static electricity. Okay. What are the general things that we see that are related to static electricity? Uh, like for an example, like even in O levels you had, if you like, if you use a polythene sheet and an ebonite rod, and if you rub them together, the ebonite rod would be charged, as I remember, positively, and the polythene would be charged negatively. Something like that, right? That's the example you had in O levels. Clear? What is the reason? What is the reason? Every material, not every, some material have loosely connected, loosely bound electrons on their surface. So when this collides with another surface, these loosely bound electrons would move to that surface. Clear? These loosely bound electrons would move to that surface. So if electrons go out from a system, if electrons go out from a system, what happens? What happens if electrons move out from a system? This system will be positively charged and the other system will be negatively charged. Okay, so this is static electricity. Static electricity. Clear? Okay, so as a result, now this is charged positively and this is charged negatively, and that charge we call the static electricity. Why do we call that the static electricity? Why do we call that the static electricity? We have two lessons in the syllabus related to charge: static electricity and current electricity. What is the difference? When this is positively charged, this positive charge stay there. When the sheet is negatively charged, this negative charge stays in the sheet. Clear? This positive charge stays in the sheet, and this negative charge stays in the sheet. Clear? They remains positively and negatively. Clear? They remains positively and negatively. So, it does not flow. That is the reason. It does not flow. They will be, I mean, unless there's an external interruption or a connection or something like that, this will remain positive forever. Okay? The charge that does not flow, we call that static electricity. Clear? In current electricity, what we discuss is the charge that does flow, right? Okay. In current electricity, we discuss the charge that does flow. In static electricity, it's stationary charge. So what are the other like things or the other practical examples that we have seen related to static electricity? For an example, like if you like walk on a carpet, okay, if you walk on a carpet, maybe a bit a long distance, if you walk on a carpet and all of a sudden, and all of a sudden, and all of a sudden, if you touch, all of a sudden, if you touch uh, some kind of a conductor, okay? If you touch some kind of a conductor, okay? What happens? You would feel a small shock. Conductor in the sense, the handle of the door, okay? If you walk on a mat, okay? If you walk on a carpet, and if you touch a metal handle of a maybe of the door handle, you will feel a small shock. Why? What is the reason? What is the reason for this behavior? Pay attention. What is the reason for this behavior? The reason is when you walk, your leg will have some loose electrons, some weakly bound electrons. Clear? Due to these collisions, okay, between the carpet and your foot, these electrons will what? The electrons will move to the carpet. Clear? Electrons will move to the carpet. Clear? The electrons will be moved to the carpet, and as a result, you will be positively charged. Sorry, if electrons go away from you, you will be positively charged. Okay. Now another thing. Now what happens when you touch a metal handle, a door handle? What happens? Now when you touch a handle, a metal handle, any metal have a what? A electron cloud, loosely bound electron cloud, right? Any metal have a lot of electrons that are, a lot of free electrons, clear, that are free to move, okay? So this is positive. To get rid of this positive nature, a bunch of electrons would flow to your body through your hand, clear? That's what you feel as a small shock, clear? Got the idea? Another problem occurs here. Why do they flow whenever they get a chance? We haven't started static electricity yet, okay? Still, we are figuring out things related to charge. I mean, it's easy to tell, okay, positive and negative, when they get together, they get neutral, but why? Okay? I'm just like giving answers to many why questions before starting the lesson, okay? So we haven't started static electricity yet, not even a definition, okay? We are just trying to first figure out why um, why charge behaves the way it is, okay? Small stuff related to charge, okay? So why does these electrons flow whenever it sees a positive charge? What is the reason? What is the reason? The reason is something like this. Okay, the reason is like it's something related to inertia, not actually, yeah, inertia and stability. That means any natural system, okay, any natural system in the world, okay, any natural system, try to comply with two natural properties. Two natural properties. What are the natural properties? Inertia and stability. Inertia and stability. That means any natural system try to implement inertia in different ways. Okay. Try to implement inertia in different ways. Clear? What are the examples? What are the examples? Uh, any natural system would try to implement inertia by different ways. For an example, something not even related with it, friction. What does the friction try? To stop the motion. To stop the motion. Then when you go to electromagnetic fields, a magnetic field tries to stop magnets from moving. Why? Inertia. All the natural systems have different methods to implement the concept of inertia. They just try to avoid changes in systems. Clear? They just try to avoid changes in systems. Okay? I mean, then the next main thing is stability. Stability. All the natural systems try to stay in the lowest energy level possible. That's why water flows from higher points to lower points. Otherwise, water had the decision of staying there, or it can go up. But water always flow from higher levels to lower levels. Okay, if you place a pencil like this, it would fall down. Why? To minimize the potential energy. So all the natural systems in the world try to minimize their energy and get stable. Clear? So even here also, something that is positively charged is not stable. Clear? Something that is positively charged is not stable. Something that is negatively charged is not stable. So whenever positive charge meets a negative charge, they try to get together and be neutral, to be stable. Clear? That's why electrons always flow whenever they see a positive stuff. Okay? Whenever they see a positive point. Clear? I mean, we don't have a very like logical reason behind that, but all we know is all the natural systems try to be stable. That's all. Clear? All the natural systems try to be stable. Clear? Okay. So next. Next, again, another example, lightning. Okay, lightning. Due to different reasons, a cloud gets negatively charged. Okay, the way in the way a cloud is formed, a cloud gets negatively charged. Then relative to the cloud, Earth gets positively charged. Relative to the cloud, Earth is positively charged. So whenever it sees a positive charge, it tries to move electrons from here to here and neutralize the system. Clear? It tries to make the system neutral. Clear? Okay? That's how things happen. So all these examples are the examples of the behavior of charge. Clear? Okay? So anyways, now in a system, if it has a static charge, a charge that does not move. Yes, definitely, whenever it gets a chance, it will move. It's a different story. But until it starts moving, it is static electricity. Clear? Until it starts moving, it is static electricity. When it moves, it becomes current electricity. Okay? Okay? When it moves, it becomes current electricity. Okay? Now, now, in your tute, Malik provide the tute in the Zoom chat. Okay, you would be able to find the tute in the Zoom chat and give the tutes in the WhatsApp groups too. WhatsApp groups. WhatsApp groups වල tubes ටික දාන්න කියන්න. Okay. So in the tube you can find, okay, in the tube you can find different terms. Okay. Well, in the tube you can find different terms. Lot of stuff you know. I have mentioned what is a positive charge, what is a negative charge, what is static electricity. When we discuss about objects, there are three types of objects. Okay, there are three types of objects: positively charged objects, negatively charged objects, and neutral objects. Okay, there are three types of objects: positively charged, negatively charged, and neutral. Okay, random stuff you anyways know. Okay. Then we have to discuss about we are still not in static electricity, we are understanding charge, okay? Next thing is, how do we measure charge? Using what do we measure charge? What is the unit? Coulombs, okay? You can remember from the SI units lesson, right? Coulombs, we use coulombs to measure charge. Clear? What is the smallest possible charge? What is the smallest possible charge? Charge of an electron, okay? Charge of an electron, okay? I mean, in the last lesson, you will learn there are some subparticles with smaller charge, with a smaller charge, okay, such as quarks, okay. There are things with much smaller charge, but they are not actually stable, okay. So the smallest stable charge is the charge of an electron, okay. So then, since it is the smallest charge, any charge of any object, okay? Since it is the smallest charge, any charge of any object is equal to some number of electrons, okay? Since electrons charge is the smallest charge, any charge that we write would be equal to some number of electrons. Clear? Then what is the charge of an electron in coulombs? Minus. Charge of an electron is minus, right? Can you remember? Charge of an electron is minus. It is a minus charge. 1.6 into 10 to the power minus 19 coulomb. Clear? Minus 1.6 into 10 to the power minus 19 coulomb. Clear? Okay. Now, so the first law that we are going to learn in the syllabus, okay? First law that we are going to learn in syllabus is Coulomb's law. Is Coulomb's law. First law that we are going to learn in the syllabus is the Coulomb's law. So what is Coulomb's law? I mean, now you would understand why it is very similar to gravitational fields. If you have a charge Q1 and if you have another charge Q2, a force will be acting between them. Clear? There will be a force between them. Clear? Then this force will be equal to what? Experimentally, they found that this force is proportional to Q1 and this force is proportional to Q2 and this force is inversely proportional to the square of the distance between them. Clear? Force is proportional to Q1, force is proportional to Q2 and force is proportional to 1 over r squared. Just like in gravity, right? Just like in gravity. So combining everything we get F equals, F is proportional to Q1, Q2 over r squared and the proportionality constant will be 1 over 4 pi epsilon naught q1 q2 over r squared. Clear? 1 over 4 pi epsilon naught q1 q2 over r squared. Clear? Okay. 1 over 4 pi epsilon naught q1 q2 over r squared. This will be the force acting between two particles. Clear? Ah. So two charged particles. Okay. What is this 1 over 4 pi epsilon? This is the proportionality constant here. Okay. 1 over 4 pi epsilon naught is the proportionality constant. Clear? Okay. Proportionality constant. So since this is the proportionality constant, okay, 4 pi we know. What is epsilon naught? Oh, I would call that epsilon first. Epsilon. What is epsilon? Epsilon, we call it permittivity of a medium. A new term. What is that? Permittivity. What is permittivity? You know from O levels, what is the, I mean, there's no other words to mention this. What is the name given to the resistance to the current? What is the name given to the resistance to the current? Resistance, right? Clear? There's no other way to mention that. Okay, we gave a name to the barrier or the resistance towards current. Okay, if a medium does not allow a current to flow, we call that the resistance is high. Can you remember? If a medium does allow current to flow easily, the resistance is low. Clear? Higher resistance and lower resistance. Clear? Ah. Just the same way, this epsilon is a property related to the medium, and it mentions whether the medium supports the static electric force or not. That means lower the epsilon, lower the permittivity, higher the support. This charge will be seen by this charge properly. So there will be a huge force between them. When epsilon increases, what happens? The visibility between these two charges gets lower. So the force between them will go down. Clear? So permittivity is a property related to the medium, and the meaning of it is whether a system supports static electric force or not. Clear? So we can call that the resistance to static electric force. Clear? Higher the epsilon, higher the resistance. Clear? Clear? Resistance to static electric force. Clear? So lower the epsilon, you get a high force. Clear? Clear? When epsilon goes down, force increases. Clear? So in this case, the lowest possible epsilon, we call that epsilon naught. We give the name epsilon naught to the lowest possible permittivity, which is the permittivity of a vacuum. Clear? Permittivity of a vacuum. In a vacuum, these charge can see them properly. Clear? The resistance is very low. So the static electric force will be very strong. Clear? So the smallest possible permittivity is there in a vacuum, and we call that epsilon naught. Clear? So value of epsilon naught is 8.85 into 10 to the power minus 12. 8.85 into 10 to the power minus 12. Remembering this is not that convenient, but you can easily remember this. 1 over 4 pi epsilon naught, you can easily remember. 1 over 4 pi epsilon is 9 into 10 to the power 9. You just put this epsilon naught and solve this, you get this. And it is much convenient to remember, right? 9 into 10 to the power 9. So remember that, okay? There's no guarantee that they are going to give this. So remember this, 1 over 4 pi epsilon is equal to 9 into 10 to the power 9. Clear? Then when you consider other media, when you consider other types of materials, they should give us the permittivity, but often they give us the permittivity using the relative permittivity. Just like they gave us the relative density, usually they give us the permittivity of different materials using relative permittivity. Relative permittivity is permittivity of the medium over permittivity of a vacuum. Clear? Epsilon over epsilon naught. Clear? Permittivity of a medium over permittivity of a vacuum. This we call the relative permittivity. So whenever required, if they give this value to get epsilon to get the permittivity, you can use k epsilon naught. Clear? So if you are okay with all these quantities, charge and the distance and 4 pi epsilon naught, if everything is okay, then you can like move forward and find the forces acting between them. Okay, you can find the force acting between them, but the only thing is in the gravitational fields it was always attractive, right? In the gravitational fields it was always attractive, but using this equation we can only get the magnitude. How can we get the direction? We know that positive to positive repels each other, negative to negative repels each other, positive and negative attracts. Clear? Positive and negative attracts. Clear? So using this we can find the magnitude of the force. Using this you can figure out the direction of the force. Clear? Got the idea? Ah. Let's move to questions. Exercise 1. Exercise 1. 3. In the third question, just finding the force on one charge would be enough. Okay. We are doing that just to like confirm the theory, that's all. And 6 and 7. 6 and 7. Ask if you have any questions, and tudes are available in the WhatsApp groups too. Well, static electricity tute, English medium. Just mention in the Zoom chat if you can't find the tute. And to get the tutes delivered or to get the past recordings or like to get added to the groups, contact this number. Note 70-154-6825. Thank you. Note 70-154-6825. Contact this number to get tutes delivered, to join the groups and like or to request for the past recordings. And the recordings are current and the tutes are available in the WhatsApp groups and the Zoom chat. Well, tute can kill. Question 3, exercise 1, question 3. What are the charges? Plus 5 micro, plus 6 micro, minus 4 micro. Plus 5 micro, plus 6 micro, minus 4 micro. Minus 4 micro. Okay. Like I would do the question only for one charge, okay? It's unnecessary to do the same thing for all three. So, I mean, all these questions are like after applying the Coulomb's law, then after that it's just a mechanics question, right? Okay. After applying Coulomb's law, then it's just a mechanics question. So in this case, I'll do the question for plus 6. Plus 5 and plus 6, they will repel each other. They will repel each other. F1. F1. Plus 6 and minus 4 will attract each other. F2. Minus 4 and plus 5 will attract each other. F3. F3. And the distance between the charge? 2 centimeters. 2 centimeters. Okay. So now you can apply the equation between this and this. F1 1 over 4 pi epsilon naught Q1 Q2 over R squared. So if they are not mentioning, we can assume that it is a vacuum. That's why I wrote epsilon naught. So here 9 into 10 to the power 9. What is Q1 plus 5 micro? 5 micro. Then plus 6 micro. 6 micro over R squared. What is R? Distance? 2 centimeters. 2 centimeters squared. Yeah. Then the next one, F2. F2, again same equation, 9 into 10 to the power 9, 1 over 4 pi epsilon naught. Q1 plus 6. I mean, although this is minus, I'm not going to write it as minus. I would just write it as plus. Why? I mean, I don't have to write plus minus here because I have properly marked the direction, right? Okay, okay. I mean, plus minus of a force means the direction, right? So since you have marked the direction properly here, you don't have to write this as write it as positive or negative. Just write the magnitude. Clear? Just write the magnitude over r squared, over r squared, 2 into 10 to the power minus 2 squared. I mean, after that it is just a mechanics question. Okay, this is 60, this is 60, then this is 120, then the resultant force would be F1 squared plus F2 squared plus 2 F1 F2 cos 120, cos 120 square root. Clear? Clear? Okay, like that you can directly find the answer, right? Okay, p squared plus q squared plus 2pq cos theta. Okay, after that it is just a mechanics question. Okay, so even static electricity, magnetic fields, everything, these are mechanics questions with some new equations. That's all. Okay, okay. I mean, until we start current electricity, everything is mechanics. Okay, think about gravitational fields. It's just just a bunch of mechanics questions with some new equations, right? Okay, it's all about mechanics. Circular motion, centripetal force, gravitational field, centripetal force, everything is mechanics, right? Okay, so that's why work on your mechanics. Okay, anyone who's not okay with mechanics, who's not comfortable with mechanics, who haven't done mechanics properly, have issues with mechanics, you have few options. Join the 27 classes, just request for the recording and try to watch 1-2 recordings per week. Okay, or else join the, like we are doing some free sessions like mechanics from beginning. We are doing a session on YouTube. Watch something like that. Or there are rapid revision classes will be happening for, I think, the 26 batch class in the future. I mean, not from me, from from someone. Okay, so join them, do something to make mechanics proper. Okay, why these are mechanics questions? Okay, you start in static electricity doesn't mean your inability in mechanics have no effect here. These are mechanics questions actually. Okay, so anyone who have issues in mechanics, do something about that. Okay, that it occurs again and again and again. Okay, the requirement for mechanics occurs always. Question 6. Anyone writing this? Still writing this? Anyone? No, right? Okay. 6 is so simple. This is 5 milligram each. This is 5 milligram. Length of the string is 4 centimeters. The question is equal charge on both. What is the charge on one object? So this is Q. This is Q and this is Q. There will be a force acting between them like this. I'll call that F1, and the weight will be like this, mg. Weight is mg. Weight is mg. And the tension you can find like this. Tension you will find like this. If this is 30, this is 30, then we can write T cos 30, upward T cos 30, T cos 30 equals mg T cos 30 equals mg T sin 30, T sin 30 equals T sin 30 equals F1. F1. T cos 30 equals mg, T sin 30 equals F1. So I can write 1, 2, 2 over 1. 2 means T sin 30. 1 means T cos 30. F1 over mg. T cancels out. Sin 30 over cos 30. Tan 30 equals F1 over mg. So I'll take mg here. M means 5 milligrams. So to convert milligrams into kilograms, 10 to the power minus 6, right? 10 to the power minus 6. Okay. I'll bring m here and g here. Tan 30 means 1 over root 3 equals F1. What is F1? F1 is 1 over 4 pi epsilon naught Q1 Q2 over R squared, right? In this case, it is Q into Q. Clear? So 1 over 4 pi epsilon means 9 into 10 to the power 9. Q1 Q2 means both charges are Q. So Q squared over, what is the distance between them? Distance between them is, this is 60, this is 60 and this is 60. So if this is 4 centimeters, this will be 4 centimeters, right? Clear? This will be 4 centimeters. So R squared, 4 into 10 to the power minus 2 squared. This is the answer. Clear? You can solve this and find Q. Go to question 7. Go to question 7. Go to question 7. Question 7. We did the same question in gravitational fields. Can you remember? We did the same question in gravitational fields, so there's nothing new in this question. Okay. We did a similar question in gravitational fields. They are moving in a circular path using their own attraction, right? So you have Q1 here. Through the center, you have Q2 here. You have Q1 here and Q2 there. So the radius here is R1, radius here is R2. Radius here is R1 and radius here is R2. Find R1 over R2. Mass here is M1 and mass here is M2. Their own attractive force is acting between them. Their own attractive force is acting between them. The same attractive force Q1 uses to go in this circle. So it uses it as the centripetal force. Clear? The same attractive force, okay? Same attractive force is used by this charge to go in this circular path as the centripetal force. Clear? as the centripetal force. Clear? So what I could do here is, I'll write all the possible equations. Not to get the answer, but I'll write all the possible equations and we'll see what we can do. They're asking R1 over R2, right? So I can write force acting between them. What is the force acting between them? This is not actually necessary to get the answer, but I'll just write 1 over 4 pi epsilon naught, charge Q1, charge Q2. So Q1, Q2 over R squared. What is the distance? R1 plus R2. R1 plus R2 squared. Okay. This is the force acting between them. Clear? Then, I again can write F equals the centripetal force of this guy, which is M2 V2 squared. Let's take the velocity of this guy as V2, velocity of this guy as V1. So M2 V2 squared over R2, and the same force is used by this guy. Same force is used by this guy as M1 V1 squared over R1. M1 V1 squared over R1. Clear? Another equation. Clear? Another equation. Okay. Again, we can write what else? What else? There are other things that we can write. Again, what we can write here? For this to happen, their periodic time should be equal, right? For this to happen, their periodic time should be equal, right? Why? They are using their attractive force to force as the centripetal force, right? So they should be always when you draw a line between them, it should go through the center, right? Otherwise, this motion can't happen, right? Assume when it comes here, if this goes here, then the force will act like this, right? Then they can't move in this direction, right? Then they can't keep up this circular motion, right? Clear? When this moves here, if this moves here, then their force is like this, right? Doesn't go through the center. Then they don't have a centripetal force anymore, right? Same thing we did in gravitational fields. Clear? So their periodic time should be equal. Clear? Their periodic time should be equal. Clear? Or else we can tell their angular velocity should be equal. Omega should be equal. Clear? Their angular velocities should be equal so that they will be in front of each other always. Clear? Clear? So I can write omega is V equals R omega. So omega equals V1 over R1, and the same omega to the other guy, V2 over R2. So these are all the relationships that I can write here. So I can do something and get the answer now, right? Clear? I can use these two. I can use these two. M2, same force. So this one is equal to that one, M2 V2 squared over R2 equals M1 V1 squared over R1. Okay. Then, if you need, you can use this too. But V1 over R1 equals V2 over R2, right? Okay. We actually don't have to go through this trouble to get the answer, but since I wrote all the equations, I'll use them. V1 over R1 equals V2 over R2, right? Okay. Otherwise, I should have used mr omega squared. That's all. Then it's done, right? Okay. If I used mr omega squared instead of mv squared over r, I'm just writing all the equations since I wrote them. Otherwise, it's not necessary to go through all this trouble. What is the question? Find R1 over R2, right? So what is R1 over R2? Again, I can write V1 over V2 equals R1 over R2. So I can write m2 over r2 into r1 over m1 equals v1 squared over v2 squared. v1 squared over v2 squared is equal to r1 squared over r2 squared. Okay. m2 over r2 into r1 over m1 equals uh, clear? Clear? So just solve this now, okay? That's all. Okay. Now you have an equation to solve, then you can get the answer. You have m2 r1 over r2 m1 equals from this side r1 squared over r2 squared. So r1 r2 cancels out with these two. r1 and r1 cancels out, r2 and r2 cancels out. So r1 over r2 equals m2 over m1, right? Clear? Clear? You don't have to go through all this trouble. Even writing these equations are unnecessary, but these are all the equations you can write in this scenario. Clear? Clear? You can write the equations for the force. You can write the equations for the centripetal force. You can write the equations for omega, angular velocity. Clear? And the angular velocities should be equal. Okay? They should have the same angular velocity. Clear? Then I just put everything together to get the answer. Clear? I use this one and this one to write this. Then I use omega equals omega for this. Get this and put it into this. Then solve it to get the final answer. Clear? Uh-huh. Okay. Anyone still writing this? Anyone? Okay. So the next concept, we have a small bunch of concepts like these, and everything is very similar to gravitational fields. Okay. So even the next term that we are learning is very similar to gravitational fields, which is electrostatic field intensity. Electrostatic field intensity. That means if you have multiple charges here and there, as a result, when you consider this point, I mean, if you have different values here and there, when you consider a certain point, okay, when you consider a certain point, a resultant force will be acting on that thing, right? There will be a resultant force on this. Clear? Ah. This resultant force, okay, this resultant force we call, I mean, I mean, this is the static electric field, right? This resultant force, okay? There are everywhere, there are different values of charge, okay? So all together, everywhere they will create a certain force, right? That is static electric field, okay? So we define something called static electric field intensity or electrostatic field intensity. What is that? It is the force exerted on plus 1 coulomb. Can you remember gravitational field intensity force exerted on 1 kilogram? Like that, we define static electric field intensity force exerted on 1 plus 1 coulomb due to a field. Clear? So if they tell that the static electric field intensity or electrostatic field intensity here is 5 Newton per coulomb, okay, that means if you place 1 coulomb here, on that a force of 5 newtons will occur in that direction. Clear? Clear? In a field, the force on a on plus 1 coulomb is static electric field intensity or electrostatic field intensity. Clear? Clear? Ah, force on plus 1 coulomb. Okay. So then what will happen if you place, I mean, if the electrostatic field intensity is 5 Newton per coulomb here, what will happen if you place minus 1 coulomb? What will happen if you place minus 1 coulomb? I mean, if if the force on plus 1 is in that direction, definitely if you place minus 1, the force will be in opposite direction, right? Clear? Whatever the direction, positive flows, negative flows in the opposite direction, right? So if the field intensity is 5 Newton per coulomb, that means for plus 1 coulomb, it is in this direction. Clear? So what happens if you place minus 1 coulomb, then the force will be in the opposite direction. Clear? Force will be in the opposite direction. It will flow in this direction, minus 1 coulomb. Clear? So that's how we identify the impact on positive negative charges. Clear? So on positive charge, the force is in the direction of the field. Okay. In negative charge, force is in the opposite direction to the field. Clear? Because the electrostatic field intensity is defined for plus 1. Clear? Then what happens? Okay. Then what happens? Then what happens if you place like a charge of plus q? What happens if you place a charge of plus q at a place with a field intensity of 5 Newton per coulomb? So per coulomb it is 5. Okay. Then on a charge of q it is E into q, right? Clear? If it is 5 per coulomb for a charge of q, how much it is? EQ, right? Or I can write 5 into q. So if you need to find the force exerted on a certain charge, what you do is you multiply the field intensity by the charge, EQ. Clear? Then what happens if the field intensity is 5 Newton per coulomb and you place minus charge here, minus Q, then the force will be EQ, but since this is a minus charge, it will be in opposite direction. So it will be 5Q in opposite direction. Clear? Force will be 5Q in opposite direction. Clear? So when it comes to electrostatic field intensity, you just get, you just apply F equals EQ. That's all. Clear? Got the idea? Ah. So in a question, if they show a field like this, in a question, if they show a field like this and if they give the electrostatic field intensity E, what you should know is if you place a plus charge here, it will move in this direction. If you place a minus charge here, it will move in this direction. Clear? And to find the force, you can use F equals EQ. Clear? To find the force, you can use F equals EQ. Clear? That's how it works. Okay? Ah. So same thing as gravitational fields, right? It's the exact same thing like in gravitational fields. Go to exercise 2. So today, like 90% of the content that we discuss will be similar to gravitational fields. Only next day we will start different stuff, things that are different from the static gravitational fields. Question 1, part 1 and part 2. Question 4, question 4, and question 7. Uh, Exercise 2, question 1, part 1. These are quite simple stuff. You have a field of 100 Newton per coulomb. Then what will be the force on 50 microcoulomb? So force will be in this direction, equals EQ, field intensity 100 Newton per coulomb, charge is 50 microcoulomb. Charge is 50 microcoulomb. This is the force. This is the force. Then in the next one, the field intensity is 200 in this direction, 200 in this direction. Again, force is EQ, force is EQ. Field intensity is 200, charge is 100 microcoulomb, charge is 100 microcoulomb newtons, but the only thing is force is in this direction, right? Force is in opposite direction. Why? It is a negative charge. Clear? Charge is a negative one. Clear? It is 100, negative 100 microcoulomb. Clear? Go to question 4. Let's go to question 4. So in question 4, there are two particles. There are two particles. Field intensity is E. Field intensity is E. So the question is just, and even in the previous question, okay, I'm not going to go to that page again. Even in the previous question, we had a similar question, right? There we neglected something. What is that? Can you remember after doing gravitational fields, now there's a own attractive force between these two? I mean the gravitational force G capital M simple M over R squared. Own attractive force, we did a similar question before. In that question also, we entirely neglected that, right? The GMM over R squared between them, gravitational attraction force. Usually in many static electric questions, we neglect that, okay? Why? These forces are very weak, okay? That's why specifically they give values like 5 milligram. Why? To make the mass much smaller. In that question also, the mass was 5 milligram, right? Okay. Why? To confirm that assumption, to confirm that, yes, we should neglect the attractive force between them. Clear? Definitely the force from Earth you should consider. Why? In that case, Earth is a huge object. It exerts a lot, enough gravity, a huge gravity. Okay? It exerts a huge gravity. Okay? But the own attraction, own gravitational attraction, we usually neglect. Okay? Clear? Ah. So here also you have the weight downward. So now tell me, so no on attraction gravitational force. Now tell me, first of all, one is plus 5 microcoulomb and other one is minus 5 microcoulomb. Clear? One is plus 5 microcoulomb and other one is minus 5 microcoulomb. Clear? Do they have an attractive force? I mean, definitely to stay like this, they should move in opposite direction, right? So, I mean, tell me, like, what is plus 5, what is minus 5? What should be the plus 5 one and what should be the minus 5 one? This should be minus 5. This should be plus 5, right? Clear? Why? When this is plus 5, the EQ will be in this direction, right? Force EQ, clear? If this is the minus 1, and since the field direction is this, EQ will be in opposite direction. Then only they will be in this shape, right? Clear? If you interchange them, they would come toward each other and collide. Clear? Okay. So plus 5 should be in this direction, then it will be pushed in that direction. Minus 5 should be here, then it is pulled in this direction. Clear? Then you have the tension here. Again, the angle is given as 30. Angle is given as 30. Clear? Angle is given as 30. Clear? And there's one more thing to consider. What is that? I mean, all the forces are now marked properly, right? Forces are marked properly. But there's one more thing to consider. What is that? On attraction, Coulomb's law, 1 over 4 pi epsilon Q1 Q2 over R squared. This is an external field. It is a different story. This field creates EQ and EQ. Okay? But since this Q and this Q, they should have their own attractive force F called what? 1 over 4 pi epsilon Q into R squared. On attractive force, Coulomb's law. Clear? There will be a force due to the field EQ. Clear? And there will be the Coulomb's attractive force. Clear? Coulomb's attractive force. Okay? Now do the question. Now do the question. You can't neglect Coulomb's attractive force. Clear? You can't neglect that. EQ, EQ and the Coulomb's attractive force. Now it's just a mechanics question, okay? After considering all the forces properly, it's just a mechanics question, okay? Nothing more than that. So, consider this scenario. This angle is 30. So this is 30. So you have T cos 30 upward, T cos 30 upward, mg downward. And in horizontal direction, you have EQ EQ, and in opposite direction you have F and T sine 30. T sine 30. Okay. So T sine 30 equals EQ minus F. So this is 1, this is 2, 2 over 1. 2 is T sine 30, 1 is T cos 30, T sine 30 is EQ minus F, T cos 30 is mg, then sine over cos you have tan 30 equals EQ minus F over mg. So F is this, F is the Coulomb attraction, 9 into 10 to the power 9, charge 5 and 5, right? Charge 5 microcoulomb and 5 microcoulomb. What is the distance? What is the length of the string? Length of the string is 0.5 meters, right? Length of the string is 0.5 meters. So this is 30 plus 30, 60. Then this is 60 and this is 60. So if this is 0.5 meters, this is also 0.5 meters, right? Clear? This is 0.5 and this is also 0.5, right? Clear? So 0.5 squared. 0.5 squared. So what is tan 30? 1 over root 3 E that I have to find. Q charge 5 microcoulomb. Q charge 5 microcoulomb minus F is this. This is F. Coulomb attraction between them. This. 9 into 10 to the power 9. 5 into 10 to the power 6 minus 6. Again 5 into 10 to the power minus 6 over r squared. 0.5 squared over mg. Mass is 2 milligrams. That means 2 into 10 to the power minus 6 kilograms. G means 10. You solve this and find E. Clear? You solve this and find E. Next, go to question 7 and then question 8. Go to question 7 and then question 8. Anyone still writing this? Someone? No, right? Question 7. Question 7. Field intensity downward E, charge Q, mass simple M, mass capital M. Only this guy has a charge. Weight is mg. Here the weight is capital Mg. This is EQ. There's a force, additional force EQ, right? That's all. There's additional force EQ. And the tension here is T. And the tension here is T. I'm applying F. Let's assume that this is going in upward direction A. If the acceleration of this guy is A upward, acceleration of this guy is A downward, then let's apply F equals ma to this guy. Downward force EQ plus mg, EQ plus mg, and minus T, EQ plus mg minus T equals ma. And for this guy in upward direction, T minus mg minus mg, T minus mg equals capital M A. So we add these two. EQ plus mg minus T here plus T minus capital Mg equals simple Ma plus capital Ma. Minus T and plus T cancels out. EQ plus mg minus mg equals capital M plus simple M A. Then the acceleration is EQ plus mg minus capital Mg over capital M plus simple M. This is the acceleration. Clear? Clear? Let's do 8 and 9 later. First, I'll do some more theory, another theory part. Pay attention, a small theory part. Quickly do finish writing. I mean, just mechanics questions, okay? Nothing new. You just have a new term called E, okay? And a new force called EQ, that's all. After that, it's just a mechanics question, okay? Okay. Okay. Anyone still writing this? Someone? Yep. Done? Still writing this? Anyone? No. Okay. Next thing, just similar to gravitational fields, okay? Again, just like gravitational fields, if you plot a graph of the behavior of field intensity around a plus Q charge, if I plot the behavior of field intensity around a plus Q charge, what happens? We did the same thing in gravitational fields. I plot field intensity around a plus Q charge. What happens? What happens? Like, how do we get the field intensity? We place +1 coulomb here, right? To get the field intensity, you should place +1 coulomb, right? force on plus 1 coulomb is field intensity, right? So since this is a positive charge, the force will be a repulsive force. Clear? Then what is the value? Coulomb's law. If the distance is r, it is 1 over 4 pi epsilon q plus 1 over r squared, right? 1 over 4 pi epsilon q plus 1 over r squared. Clear? Q plus 1 over r squared. Okay? Uh, so the same law, Coulomb's law, instead of Q2, you have plus 1 here. Then when you make Q2 plus 1, you get the field intensity, not the force, right? Why? Force on plus 1 coulomb is field intensity. Clear? So now as you see, this part is a constant, this is a constant, it depends on r squared. It's inversely proportional to r squared. When r is 0, it chooses to infinity. And I should choose a direction. Why? Field intensity is a force. So you should, it's a vector. So for the graph, you should choose a direction, right? I will choose this as the direction, positive direction. I will choose this as the positive direction. Then in this side, it is positive. Why? It's in that direction. When r is close to 0, this shoots to infinity. When r increases, field intensity drops. When r increases, field intensity drops. Clear? In this side, it's the same behavior but negative, right? Why? In this side, again, forces are repulsive, so it's in this direction, which is the opposite direction to my positive direction. Clear? It is the opposite direction to my positive direction. Clear? So it's the same behavior but negative. Clear? Same behavior but negative. Clear? Uh, like that we can plot graphs too. Okay? Like that we can plot graphs too. Like not today actually, next week we'll draw a lot of graphs in different systems. What happens when you have two charges q and q? What happens if it is plus q and minus q? What happens if it is plus 2q and minus 3q? The behavior of the field intensities we are going to plot next week. But the just mentioning, it's just like gravitational fields, right? Clear? Okay. Then again you have a term called resultant field intensity. What is resultant field intensity? If you have multiple field intensities at a certain point, if you have multiple field intensities at a certain point, vector sum of them is the resultant field intensity. Clear? Vector sum of them is the resultant field intensity. Clear? It is the vector sum. Okay? And when you calculate the resultant field intensity, if it is 0 at a certain point, when you calculate the resultant field intensity, if it is 0 at a certain point, okay, if the resultant field intensity is 0 at a certain point, we call that a neutral point. Clear? If the resultant field intensity is 0 at a certain point, we call that the neutral point. Clear? So this is the basic story. Okay? So we can do more questions. Okay? So I'll give you a set of questions. Let's try exercise 2. Let's try exercise 2. Question 8 and 9. And then exercise 3. Exercise 3. Question 2 and 4. I'll give you the interval and be here by 5:20 and start doing these questions. Exercise 2, question 8. Exercise 2, question 8. Exercise 2, question 8. The electric field between two large vertically charged parallel conducting plates has a field intensity of 200 Newton per Coulomb. An object of mass 5 milligram carrying a charge of 10 microcoulomb is placed in the field and dropped. The object is released near the positive plate. Mark the force acting on the object. Draw the direction which it moves. What is the horizontal displacement of the object when it falls 20 meters vertically? Uh, this is positive. This is negative. You have a field of 200 Newton per Coulomb in this direction. There's a field of 200 Newton per Coulomb in this direction. And we will place plus 10 microcoulomb here, plus 10 microcoulomb here, plus 10 microcoulomb here, and 5 milligram. So the field is in this direction. Field is in this direction. And there's a weight. So as a result, on this object, there will be two forces, right? One is the weight. One force is the weight. Okay. One force is the weight acting on this. Clear? And the other one is the electrostatic force, EQ. Clear? Mg and EQ. Clear? So as a result, it will move in this direction, right? Clear? As a result, it will move in this direction. These are the forces. This is the direction. Draw the, what is the horizontal displacement when the object falls 20 meters vertically? So when it falls 20 meters vertically, what is the horizontal displacement x? So downward, s equals ut plus half at squared. It falls 20 meters vertically. Starting velocity 0. Starting velocity 0 plus half acceleration 10. Gravitational acceleration 10. Again capital T squared. Clear? Half 10 T squared. Clear? Then 0 to 0 cancels out. T squared equals 2 squared. T is 2 seconds. Now let's apply F equals ma horizontally to find the horizontal acceleration. Horizontal force is EQ. Horizontal force is EQ. What is EQ? E means field intensity, 200 Newton per Coulomb. Q charge is 10 microcoulomb. 10 microcoulomb equals mass. Mass of the object 5 milligram. 5 milligram, that means 5 into 10 to the power minus 6 when converted into kilograms into A. So what is the acceleration? 200 10 10 to the power minus 6 over 5 into 10 to the power minus 6. 10 to the power minus 6 and 10 to the power minus 6 cancels out. You get acceleration as 400. You get an acceleration of 400. Then apply S equals ut plus half at squared in horizontal direction. Horizontal displacement x, starting velocity 0 plus half, acceleration 400, time 2 seconds, time 2 seconds. You get 800 meters. So it moves 800 meters horizontally. Clear? It moves 800 meters horizontally. Clear? Let's do 9 later. You can try it at home. I'll go to exercise 3, question 2 and 4. I'll move to exercise 3, question 2 and 4. try all the remaining questions at home and ask me next week. I'll discuss those questions at the class. Exercise 3, question 2 and 4. And again, one more thing, like now the 25 batch classes are over. So we have to like change plans a bit for the 26 batch. Things like whether, what about the revision? What are the changes that should happen to the paper class? What are the changes that should happen to the paper writing sessions? We have to make it more like aligned with everything, and even for these classes we should like do few changes, so there should be some changes happening. Okay, so we need some information about that too, the possible dates. Okay, like just let me, I mean, I just need a rough idea from the physical students, like the students who have classes on Monday evenings. Students who have classes on Monday evenings, properly raise your hand. And the people who have classes on Friday evenings, have classes on Friday evenings. And like, yeah, and Tuesday evenings. People who have classes on Tuesday evenings. Okay. Just let me know. Okay, when I come, just let me know what are the classes you have on Fridays and Mondays. Uh, and we have to check uh, like what should be the paper writing slots and all. Okay. Exercise 3, question 2 and 4. Exercise 3, question 2 and 4. Exercise 3, question 2. A square ABCD whose side length is 2 meters, side length 2 meters, charge +5, +8, -6 placed at vertices ABC respectively. What is the electric field intensity at its center? So +5, +8, +5, +8, -6. +5, +8, -6. What is the electric field intensity at its center? Quite simple. What should you do? Uh, Here, I mean, if you place a +1 coulomb close to a plus charge, a positive charge, it is a repulsive force, right? That means field intensities are away from positive charge, right? Field intensity is away from positive charge. Why? Field intensity is the force on a +1 coulomb. Clear? So the field intensity from this +5 would be in this direction. Clear? E1, field intensity from this +8 would be in this direction, E2. And when you consider a negative charge, if you place +1, it will be attracted, right? It will be attracted. Clear? So the field intensity would be towards the minus charge. So for the -6, it will be towards that minus charge, E3. Clear? Field intensity would be towards that minus charge. Clear? E3 is towards that minus charge. Clear? So, I mean, I can apply Coulomb's law. E1, 1 over 4 pi epsilon Q, and I place 1 coulomb here over R squared. And in a square, this is 2, then this is apply Pythagoras 2 root 2, then half of it would be root 2. Half of it would be root 2. So E1 equals 9 into 10 to the power 9. What is the charge? 5 micro. 5 micro over 1 over 4 pi epsilon 9 into 10 to the power 9. This is 5 into 10 to the power 6. What is R squared? Distance root 2. So it is root 2 squared. Then what about E2? E2, 9 into 10 to the power 9. What is the charge here? 8 micro over R squared. Again the distance is root 2 squared. Then what about -6? E3. E3, 9 into 10 to the power 9. Here the charge is 6 micro. The distance is again root 2 squared. Root 2 squared. Then uh, consider the center. In this direction you have E1 plus E3. E1 plus E3. In this direction you have E2. Now to find the resultant, just apply the Pythagoras law. Why? These are perpendicular to each other. These are perpendicular to each other. So the resultant field would be E2 squared plus E1 plus E3 squared square root. Clear? This is the resultant field intensity. Clear? Resultant field intensity. Go to question 4. If you are done with question 4, go to question 3. Go to question 4, and if you're done with question 4, go to 3. Okay. Uh, like these directions, there's a question how I mark them. I mean, it's quite obvious. I mean, you take +8 charge, okay? You take +8 charge. What is the field intensity due to +8 charge? Field intensity means force. Field intensity means force on 1 +1 coulomb, right? So if you place a +1 coulomb here, what would be the direction of the force? This direction, right? This will be the direction of the force, right? The repulsive force, clear? That's why I mark the field intensity due to +8 in this direction, away from +8. Then field intensity due to +5, away from +5. Field intensity to -6, towards -6. That's how I mark them. Clear? Clear? Then I apply Coulomb's law to find the values. Coulomb's law in the means +5 and +1. I applied Coulomb's law to +5 and +1. Here +8 and +1. Here -6 and +1. I apply Coulomb's law to for two charges, and the charges I'm considering is the required charge and plus 1. Why plus 1? Field intensity is defined for plus 1 coulomb. Clear? Got the idea? Then I have three vectors. Two are parallel, so I can directly add them as E1 plus E3. And the third vector is perpendicular. So I can apply the Pythagoras law. I can draw a vector triangle, apply Pythagoras law, and get the resultant. Clear? Clear? Ah. Just let me know if there's any other issues, okay? Still writing this, someone? Anyone? Still writing this? Quickly finish. Let's go to question 4. Let's go to question 4 next. If you're done with 4, go to question 3. Try to do the questions in the given time because a lot of concepts are similar to gravitational field, so you are capable of finishing the questions, okay? In some lessons, you are not capable of finishing the questions because the theory points are new. These are not actually new, right? It's same thing happened in gravitational. Okay. Uh, question 4. Find the distance to the from Q2 to the neutral point line joining Q1 and Q2. This is Q1 and this is Q2. Q1 and Q2. Q1 is plus 9 microcoulomb. Q2 is minus 4 microcoulomb. Okay, we have to find the neutral point. Neutral point on the line joining Q1 and Q2. So the first thing is we have to find the placement of the neutral point, right? That means, can I have a neutral point at the center? Neutral point means resultant field intensity is 0. Can I have a neutral point at the center? No, right? I can't have a neutral point at the center. Why? Field intensity is away from a positive charge and field intensity is towards a negative charge. See? Field intensity is away from a positive charge and it is towards a negative charge. Clear? So the resultant is in this direction then, right? See? So there's no way that you are getting 0 here, right? Clear? There's no way that you are getting 0 here. Why? Both field intensities are in same direction. Field intensity due to positive charge in this direction, field intensity due to negative charge is also in this direction. Clear? Then let's check this side. Field intensity due to plus 9 is in this direction. Field intensity due to minus 4 towards minus 4. So here it's possible, right? Plus 9 is in one direction, minus 4 is in another direction. Clear? Field intensity due to plus 9 is this direction. Field intensity due to minus 4 is in that direction. But what is the problem? What is the problem here? Here still we can't get a neutral point. Why? Plus 9 is always powerful. Plus 9 is a larger charge than minus 4. So plus 9 will create a higher field intensity here. And at the same time, distance to plus 9 is lower. So we know that field intensity is proportional to the charge, inversely proportional to the distance. Plus 9 is winning from Q and R both. To have a 0 here, okay, to have a 0 here, this component and this component should cancel out. Okay? But the problem here is, in this side, plus 9 is always winning. Clear? Why? Distance is small, charge is large. Clear? In this side, plus 9's field intensity would be always larger than minus 4's one. Clear? Let's check this side. In this side, the field intensity from plus 9 would be away. Field intensity from minus 4 would be towards. But in this side, a neutral point is possible, right? Why? In this side, it's closer to minus 4. But plus 9 is the large one. That means in this side, this one will be larger. Field intensity due to Q2 can be larger due to the advantage from the distance. Clear? But in this side, plus 9 has the advantage due to the size of the charge. So in this side, minus 4 has the distance advantage, plus 9 has the advantage due to the magnitude of the charge. So the advantages can be cancelled out, right? Clear? As a result, and in that side, there's a possibility of 0 field intensity. Clear? In that side, there's a possibility of 0 field intensity. Clear? So, neutral point is, if this distance is x, if this is E1, if this is, field intensity due to plus 1 is in that direction, E1. field intensity due to Q2 is E2, it is toward because it is minus. Clear? So to have a zero field intensity, E1 should be equal to E2. What is E1? E1 is 1 over 4 pi epsilon. What is Q1? 9 microcoulomb. And to find field intensities, what we keep is 1 coulomb there, right? Over r squared. What is the distance? This distance is 10 centimeters plus x, right? So 10 centimeters plus x. Overall distance is 10 centimeters plus x squared. Clear? Then you have 1 over 4 pi epsilon naught. What is the charge? 4 microcoulomb. And we keep 1 coulomb there to find the field intensity over r squared. The distance is x. Clear? So a lot of stuff would cancel out. 1 over 4 pi epsilon. 10 to the power minus 6 will cancel out. I'll take everything to that side. 10 into 10 to the power minus 2 plus x squared over x squared. Here 9 over 4 and get the square root. And get the square root. 3 over 2. 3 over 2. If you get the square root in this side, it becomes 10 into 10 to the power minus 2 plus x and x here. Now you can solve this and find x. What is the value of x? Someone? 20. 20 centimeters. We get the answer of x as 20 centimeters. 20 centimeters. තව දැන් අපි මේ උදේට එහෙම උගන්වන්න ගත්තොත් මේ බැරි කට්ටිය කවුද ඉන්නේ? Students who can't like join like morning classes. Anyone? Morning class, I mean, the means you have to go to school. People who have to go to school? Really? Only 2 from the class, right? Properly raise your hand. Properly raise your hand. Okay, okay. I mean, it can't happen from the same school, right? I mean, only two having the issue. Anyways, now the attendance problems are over, right? Now the people who has the 40% attendance, they would have that. At the end of the day, what they check is the 40% attendance, right? Not an 80%. So the morning classes are a possibility, right? Yes, right? Okay. So let's move to some new stuff. Okay. Next, what we are going to do is and specifically after the class, just mention me the issues you are having with the schools. Okay, if you have to go to the school, need to know that. Okay. Um, so the next new thing is, okay, now we are entering the new areas of static electricity. Okay. So in that, like, if we take, okay, if we take a positive charge, okay, like or positive or negative, any charge, there's an important fact we should consider before moving into the next part, which is the charge distribution of an object. Because in gravitational fields, we didn't have that issue. Why? Distribution of mass means the object, right? I mean, there's no separate mass distribution. It is the shape of the object. Okay? So if they tell that this is a sphere, that is the distribution of mass. Clear? If they tell that this is a something like this, that is the distribution of mass. So the distribution of mass is visible, right? Distribution of mass is something quite obvious and it is visible, right? Clear? It is entirely visible. Clear? But uh, charge, not obvious because charge can go through an object, so we don't know exactly how the charge will be distributed in that object. So to move forward, until now we were discussing about a point charge. That's all. We have to figure out if we take an object, what will be the charge distribution before moving into further parts. Clear? Ah. So, so the next thing is like this. We take a, like, consider, first consider a, I mean, when you are considering the insulators, no issue, okay? Why? Insulating objects. Insulators means, I mean, the things that are not conductors. Okay, not actually insulators, non-conducting materials. There's no issue. Why? If you give a charge to a non-conducting material, the charge can't flow, so it will anyway stay there. Charge distribution is not an issue. If you put a charge, if you place the charge in whatever the way you like, it will stay there because in a non-conducting material, the charge can't go from here to there. Clear? So there's no point of talking about the charge distribution of a non-conducting material. It is equal to the way you provide the charge. Clear? Clear? If you place all the charge at the center, it will stay like that. Why? It's not possible to move. Clear? So what matters is the charge distribution of conductors. Clear? What matters is the charge distribution of conductors. So you get a conductor. Now you give a bunch of charge to this. Now again, all the natural systems try to be as stable as possible, right? Now when they are close to each other, there's a lot of repulsive forces acting against each other, right? There's a lot of repulsive forces acting against each other. They will be They will be pushed away from each other, right? Because it is a bunch of positive charge. So they will be pushed away from each other. Clear? So they will be pushed away until everyone reach the surface. They will be pushed away until everyone reach the surface. And if you have more charge here, there will be a lot of repulsive forces here. So the charge will be pushed away until what? Until it is equally distributed, right? I mean, this is the most stable state, right? All the charge will be pushed to the surface due to repulsive forces, and they will be distributed uniformly such that there's no resultant force on anyone. Clear? They will be pushed away from each other until everything is distributed uniformly. Only when everything is distributed uniformly, then there will be no resultant force on anyone. Clear? Got the idea? Ah. So now the next thing is, okay, now is this clear? Is this clear? Okay. So in a uniform object, distribution is uniform. That's the story. No big issue there, right? Charge will be distributed uniformly. Clear? But take something like this. Uh, Consider a shape like this. Consider a shape like this. Now what? Now what? Now the distribution must change. And the thing is, when you consider pointed edges, like in an antenna, okay, you know that lightning strikes a lot on antennas, right? Because it's a pointed place, right? So pointed conductors contains more charge than uniform areas. Clear? Why? What is the reason? This is the story. Here you can have only small number of charge, and in a pointed place you will have a lot of charge. So charge will be distributed such that there's a lot of charge on a pointed place. Why? What is the reason? Reason is this. You take a surface like this. If you place two charged particles like this, see, both are visible to each other a lot. And they are visible through what? Through a vacuum or air. Air is almost equal to a vacuum, right? And we know you have the maximum forces when you are in a vacuum or air. So in a surface like this, charge is visible to the other charges through air. So there's a lot of repulsive forces. So they can't stay close to each other. Clear? But when you take a pointed place like this, you have this charge here and this charge here. They are not visible to each other through the vacuum. They are visible to each other only through the conductor. And conductors provide the weakest possible field intensity. Okay? The field intensity through a conductor is almost zero. Okay? Field intensity through a conductor is almost zero. Okay? So when you see through air, you have a maximum repulsive force. When you see through a conductor, you actually can't see each other. Electrostatic field is very weak through a conductor. Clear? It is very strong through a vacuum. It is very weak. It's extremely weak. It's extremely weak through a conductor. Clear? Clear? Then, like, it's not only this. When we discuss about, it's not a 2D diagram, right? It's a 360 3D diagram, right? It's a 360 3D diagram. Clear? So as a result, you can have a lot of charges around that. Clear? Clear? Ah. So in pointed areas, you have a more charge, okay? A higher charge distribution. In uniform areas like this, you have a low amount of charge. Clear? Ah. That's the charge distribution. Clear? Clear? That's the charge distribution. Got the idea? Ah. And, okay, like the in other parts, in the sense like I mean, a very nice example is the antenna. Right? You have the cloud here negatively charged, and you have the earth relative to the cloud. Earth is positively charged, but it is a uniform surface, so there's a weak positive charge, right? But when you consider an antenna, due to this pointy shape, it contains a lot of positive charges. Clear? Clear? So when the cloud tries to find a path to be neutral, it sees a huge positive charge here. Clear? As a result, it considers this as the easiest path to flow. So it strikes here. That's why even in lightning conductors, you have 3 pointed wires like this. Clear? Clear? Even in lightning conductors, akunu sannayaka, okay, they have 3 pointed uh, wires like this to have a higher charge density. Then the cloud recognize this as the easiest path. Clear? Because negative charge tries to figure out where can I find the most amount of positive charge. Clear? Then the lightning strikes there, hoping to be neutralized as fast as possible. Clear? Just like the water flows to the lowest point. Okay? If you have multiple levels, at the end, all the water will try to flow to the lowest point possible, right? Clear? Ah. So this is the story about charge distribution. Is that clear? It's the story about charge distribution. And uh, there's one more thing that you should learn. That is, like this is, I mean, this is not fair to teach it here, but in static electricity lesson, you have that usual issue. Usual issue in the sense like to learn the things, to learn this stuff, I mean, to learn the next stuff we are going to learn, you need this. And to understand this perfectly, you need them. Okay? So the problem is, I mean, these are not sequential lessons. Content now helps the content later, and content later helps the content now. Okay? So as a result, static electricity, you would understand chapter wise. That means when we finish a whole bunch of things, now everything will be connected, then you will understand. Okay? Because it it's not sequential like in other lessons. Okay? In other lessons, you don't need later parts to understand this, right? But it's not, in static electricity, yes. Okay? So you would understand things properly, things will be connected later. Okay? So another similar thing is potential. Potential I haven't defined yet. We haven't even defined the electrostatic potential yet, right? We don't know a equation for the electrostatic potential, okay? But on the way to define that, we have to know that a conducting surface is a equipotential surface, okay? That we have to know. Without that knowledge, we can't develop the next theory points. So later when we define potential, you will understand this. For now, you have to know, or you have to assume that the surface of a conductor is an equipotential surface. Clear? But I can slightly explain that using your O-level knowledge. You knew, from O-levels you knew that when there's a potential difference, what happens to the charge? They flow. That you know from O-level, right? When there's a potential difference, charge flows from one point to another. Clear? When there's a potential difference. Clear? So if you have lot of charge here, here the potential will go up. So what happens? This charge will flow from higher potential to lower potential until the potential drops down and potential becomes equal everywhere. So from that knowledge you should understand this is a conducting surface. There until the potential is equal everywhere, charge will keep moving here and there. Okay, charge will keep moving here and there until you have the same potential everywhere. Clear? It will keep flowing. Clear? So as a result, any conducting surface is an equipotential surface. Clear? That you have to know for the next stuff that we are going to discuss. Okay, is that clear? Okay, any conducting surface is an equipotential surface. Okay, so the next part is electric field lines, an entirely new thing. So from next week onwards we have the new stuff. Today I finished the things that are related with gravitational fields. Okay, so it's 6:20. I'll start the heat lesson around 6:35. I'll start the heat lesson around 6:35. Yeah, finish all the questions up to exercise 3. Okay, finish all the questions up to exercise 3.